So now we are going to work on free damped vibrations. Let me go ahead and write that down up here. So now we are going to look at free damped vibrations. Okay, so we are still going to assume that there will be no external forces acting on the system, with the exception of damping. So in this case, the differential equation will be the following. It will be mu double prime, so we still have the force of gravity. Now we're going to add gamma times u prime, which are the damped forces, plus ku, which is the force of the spring. And that's all going to be equal to 0 since the system is free. No external forces are present or acting on the system. Okay? And again, this is going to be where m, gamma, and k, okay, are all positive constants. Positive constants. Okay, so upon solving the roots of the characteristic equation for the equation that we have up here, we end up with the following two roots. So r comma 1 comma 2 is going to be set equal to negative gamma plus or minus the square root of gamma squared, okay, minus 4 times mk, all divided by 2m. All right, so that's what we end up having as our roots. And so we actually have three cases that we have to pay attention to. And so these are three cases that you would have to test for yourself in order to determine which path forward would be the most appropriate. So let's talk about the first case. The first situation is where the value underneath the square root sign is actually equal to 0. Or, to put it this way, if gamma squared minus 4 times m times k, which is exactly the value you see under the square root sign that you see up above, is equal to 0, then we have a very special case that we need to work through. Okay, and there's two more cases like this. So in the first case, we will actually get a double root out of the characteristic equation, and the displacement at any time t will actually give us this equation, which is u of t, which equals c1 times e to the minus gamma times t, all divided by 2 times m, plus c2 times t e to the minus gamma t, all divided by 2m. Okay, and so notice something though, that as t goes to infinity, the displacement will approach 0, and so the damping in this case will do exactly what it's supposed to do. So anyway, when gamma squared minus 4mk equals 0, this is called critical damping. Okay, so this whole situation is known as critical damping. Okay, and so this implies a few things. So first of all, like we said before, this implies that gamma squared minus 4 times m times k is set equal to 0, or was found to be equal to 0. And so taking this a few steps further, solving for gamma squared, and this being set equal to 4mk, we can go one step further and solve for gamma, and this is going to equal 2 times the square root of m times k. Okay? And what this is equal to is given the name as gamma CR. Okay? And what this is referring to is the damping coefficient that gives um, what is also known as the critical damping coefficient. Okay? And so that's what CR here is referring to, the critical damping coefficient. All right, so that's it for case 1. And now let's go to case 2. That's the situation where gamma squared minus 4 times m times k is positive. Okay. And so by working through this root a bit more carefully, we can find a few observations out of this. Now this one is considered to be called overdamping. Just so you know, the situation is known as overdamping. So I could say this implies overdamping. Okay. And I will cover more of overdamping here in the next video.